grade 12 chemistry. This is the last video in Unit 1. It's talking about types of crystals. We're going to talk about 4 different types of crystals here. We're going to talk about ionic crystals, molecular crystals, covalent network solids, and then metal crystals, and how the metal crystal theory explains the properties of metals, those unique properties that metals have. So, quick review of intermolecular forces. This is from the last video. Ionic forces are the attraction between ions. They're very strongly polar, right? Sodium is positive, chlorine is negative. It's an attraction, electrical attraction. It's really just electrostatic attraction. Please keep in mind, those ions are still separate. They are separate things. They're just attracted by electrical force. Then there's dipole-dipole forces, attractions between the positive and negative ends of dipoles. So these are held together by a bond, but between them there's this positive-negative, delta-positive, delta-negative attraction. So that green is trying to show that they're attracted to each other, positives to negatives. So positives to negatives, there's attraction, but a positive and a positive, a delta positive will repel itself. And that means that more polarity is a higher dipole moment, more force, higher melting point. And the thing about these guys is there's also the H bonding capacity. If you have an oxygen attached to a hydrogen or a nitrogen attached to a hydrogen, that hydrogen becomes very positive, very delta positive. And so it can coordinate to lone pairs on a different atom and becomes a strong force. And then every single molecule has London dispersion forces. It can have these and London dispersion forces at the same time. Bigger becomes stronger. So bigger is a bigger or a longer molecule makes a stronger London dispersion force, but it's a very weak interaction when compared to dipoles and ionics. Right? Water has hydrogen bonding capacity, boils at 100 degrees. You have to get up to heptane to get near water's boiling point. So that's 7 carbons and 16 hydrogens together to match just 1 oxygen and 2 hydrogens. That's a review of intermolecular forces. Talk about types of crystals. So different solids make different types of crystals depending on the bond type, what kind of intermolecular forces are there. We're going to focus on crystals. The first type is ionic crystals. So salt, potassium nitrate, ammonium chloride, they have these lattice structures. Ions are held together by these very, very strong electric forces. Very strong electric forces. But they can be weak in 2 specific cases. So here's a diagram of salt. This is the structure that sodium chloride will adopt. 1 sodium, 1 chlorine, and each sodium is surrounded by chlorines. Each chlorine is surrounded by sodiums. It's very, very strong because it's a sum total of many individual forces. It's kind of like a tug-of-war team all pulling at the same time. You get a very strong attractive force in these directions, in these specific directions. So it's very hard to pull apart, very hard to melt. Salt melts at 800 degrees Celsius. But there are 2 specific cases where it gets weak. The first is something called cleavage. And what happens is the strength comes from this regular arrangement of atoms, and they're very, very regularly arranged, but as soon as you break it, even by 1 atom, if you move it by 1 atom, suddenly instead of positives attracting negatives, you have a positive next to a positive, a negative next to a negative, and a positive next to a positive, and a negative next to a negative, and the whole thing will just split right along that plane, right along the plane of cleavage, and it's literally called a cleavage plane. This is a salt crystal, and I guess it's been dropped a couple of times. You can actually see those perfect 90-degree cleavage planes through it. Perfect 90-degree cleavage planes. And the other thing that makes them weak is water. When water attacks salt, it will take these individual ions and individually pull them away because they're strong together, but if they're separated one at a time, the water can grab them. And the best video to show that is this one from the Museum of Nature. It'll show you water and salt and how the water will dissolve the salt. So you can watch this video here. There's a salt crystal. There's the water. You see them kind of dipole bonding with each other. the hydrogen bonding with each other. It's going to go through the positives and negatives. So water has this positive side and this negative side. Positive side, negative side. The sodium chloride has a positive side and a negative side. And so the water can actually, because it has different positives and negatives, a few water molecules can come in and just kind of gang up, bring their positives near the negative, and just pull that one ion out, right? One ion. The strength, remember, of these things comes from the arrangement, the regular arrangement of positives and negatives all supporting each other. But if they're just grabbing one at a time, they can pull the whole thing apart. Same thing happens with the positive. The negative side of the water, the oxygens, will pull apart the sodium, and so they create these things that are called hydration spheres around the ions. And so the water can just pull away individual ions, and over time it can go in and just kind of like take apart the entire crystal. So that's how salt dissolves in water, and that's how most ionic compounds dissolve in water. Some ionic compounds actually do a reaction with the water in order to dissolve better. They actually put the water as part of their lattice in a weird kind of way, but that's more advanced chemistry that we're not going to talk about. So most will dissolve easily in water due to ion size and charge, but some won't, like iron oxide won't. A few like silver chloride won't dissolve in water. Basically, those ions are so strongly bound to each other that that the water can't do its little pull apart thing. Can't pull it apart. So that's salts dissolved in water. This is also why there's a maximum limit of how much of a certain salt you can dissolve in water. Basically, the water is busy surrounding the negatives and the positives and doesn't have enough strength to pull other negatives and positives away. So yeah, ionic crystals are very, very strong, but they are weak to cleavage planes. They will fracture, and they will dissolve easily in water. Next, we're going to talk about molecular crystals. So I'm going to pause. Molecular crystals. Molecular crystals are, as you can imagine, molecular, so they're not ionic. Some examples of these are sugar, ice, iodine, dry ice. So ice, for example, is a really good example. Ice is still just liquid water. It's still just H2O. It's still a bunch of H2Os. But they're arranged with intermolecular forces between the hydrogens and the oxygens. So remember that the oxygens are negatively charged, the hydrogens are very positively charged. So there's this hydrogen bond between this oxygen and this hydrogen. Notice that they're not touching, but they are coordinating to each other. And then that oxygen coordinates to this hydrogen coordinates to that oxygen, and so on and so forth. And you end up with this structure that looks like little hexagons. This is the key to understanding why ice floats on water. That hexagon has a bunch of empty space in the center, and it makes the solid form of water less dense than the liquid form, because the liquid form can, arrange themselves more tightly. It also helps explain why snowflakes are hexagonal. If you ever see a picture of a snowflake, it's always a hexagon because it grows in this hexagonal crystal structure. And we've got this really cool super short video of someone that sets off a firework under ice. Clearly this ice crystallized very nicely, very slowly, because, poof, there's a hexagon. And I'll link both these videos down in the description. That one and the How Water Dissolves Salt video will be linked in the description. So these are held together by intermolecular forces. They are still individual atoms, so you can still pick individual atoms away from it. And here, for example, is dry ice. Dry ice orients itself like this. Here are sucrose molecules. And you see that they orient themselves in the lowest energy conformation. It's almost like one's like this and the other one's like this, kind of, and then the next one's like that, and the next one's like that. And they end up making a regular arrangement, a regular pattern. Here's glucose, or here's sucrose, and you see the positives and negatives as reds and blues. And here's an animation of water dissolving sucrose. So you see the reds and blues, and then the water comes in. Same exact process as the salt. They will surround it and coordinate negatives to positives, negatives to positives, positives to negatives, positives to negatives, and just take that individual piece of sucrose away from its buddies. So you see that's the crystal, and they'll just get pulled away like that. This means that if you're careful, you can actually create sugar crystals or salt crystals and grow them by dissolving a bunch of sugar or salt in water and then slowly taking away the water, because the crystals will, the molecules will naturally arrange themselves into the perfect shape over time. So what you can do to grow your own crystals is just let the water evaporate away from something that is holding a bunch of solid. You can look up instructions online. There's a ton of instructions for how to grow your own crystals of sugar or salt or whatever you have. And you can get these cool looking crystals. Here's some pictures under a microscope. Here's sugar under a microscope and salt under a microscope. You can see the salt, that real nice cube shape. If you actually really carefully take a look at salt, like on your fingertip even, you can actually see the cube shapes if you've got good eyesight. Sugar takes more of a hexagon kind of shape because because glucose has this kind of hexagonal shape, and it stacks up into these hexagons, right? That lends itself to this shape as they pack in the most efficient way possible. Other ones will pack in different ways, so sometimes we get these like octahedrons and stuff like that. It's very, very cool. This is very the properties of these typically depend a lot on their size. So same with the melting point and boiling point. Generally these are quite soluble in water because they're being held together with intermolecular forces, but something like CO2 is not very soluble in water. And melting point and boiling point, same thing. Carbon dioxide, right? It turns into a gas at minus like 100 and something degrees Celsius. Meanwhile, sugar stays solid at room temperature. It's really, really highly dependent on what kind of bonds we're talking about here. That's molecular crystals. Maybe one fun one is iodine crystals. So let's look at iodine crystals. This is iodine, elemental iodine. It's a solid, and it makes these crystals. These crystals, that's what they look like. But it can only be held together with van der Waals forces. Right? It's just iodine and iodine, I2. And so there's no polarity, so it's only London dispersion forces holding it together. So it is such a low boiling point that it actually melts and turns into a gas, even at room temperature. It's very, it stays solid at room temperature, but it gives off a lot of gas. It's very easy to get it into the gas phase because it is held together purely through London dispersion forces, just like dry ice is. So that's molecular crystals. Our next thing is my favorite, which is covalent network solids. So I'm going to pause and set that up. And the reason that I like them so much is that they are all bonded to each other. This is why they're called a network, a covalent network. There is an actual bond, an actual shared electron system between every single one of the atoms here. So it's not the same as these guys where there's an intermolecular force, or these guys where there's an ionic attraction between them. These are actually hooked together through electron pairing, which you can imagine makes a very strong structure most of the time. And this is one gigantic molecule, one huge molecule. So think about a pane of glass. I'm sure you have a pane of glass somewhere, like the glass that's covering my phone. Or the glass that's making up this Erlenmeyer flask. Right? That piece of glass can be thought of as one gigantic molecule. This is what glass looks like. It's kind of this amorphous looking molecule thing. Versus quartz, which are actually SiO2. Both of these are SiO2. This one's just very regularly oriented, and this one is a little bit funkier. But they are both solids, and they're both very strong, hard to break. They do suffer from the same problem that the ionic crystals did. Actually, any crystal does, is that the strength comes from the repeating nature of the bonds, and this strength comes from the repeating nature of the bonds. And so if you move it out of alignment, you end up with cleavage. This is why glass will shatter. You know, you'll end up with stuff like that in the cleavage planes. That's true for all of these, especially stuff like quartz, where you have this really, really, really nice regular arrangement of atoms. And here's some for carbon. Diamond is just carbon tetrahedrally bonded to other carbon. It's all single bonds, tetrahedral bonds. Then there's some funkier ones like graphite. Graphite are sheets of carbon that is in this flat orientation. If you looked at the previous video about Vesper, the way to get flat is to have 3 electron domains. So basically, each carbon has 1 double bond and 2 single bonds coming off of it to make 4 bonds, and so it's got this flat arrangement. This is why graphite, which is the stuff that's in pencils, it comes off so easily on the sheet of paper. You're actually just taking off basically a sheet of carbon every time you drag the pencil across the paper. It's also used as lubricants. This is used as lubricants in industrial settings because the sheets slide across each other very, very, very easily. Yeah, so that's graphite. Then there's funkier ones like the buckyball, Buckminster fullerene, which is carbon in a little cage structure, and a carbon nanotube that can be made arbitrarily long. It can be made as long as it needs to. And as you can imagine, because it's actual bonds, actual electron sharing bonds, this becomes very strong because it is actually sharing electrons the whole way along. They're very large. They're often insoluble because of just the size. So, you know, try to dissolve this. Water would have to surround the whole thing. But water is attracted to glass, right? It's attracted to glass because it's silicon and oxygen. And so you've got these polar little things that it can hook onto. You know, you can try this out yourself. If you have a glass and a plastic cup, the water will crawl up the sides of the glass and won't crawl up the sides of the plastic cup, depending on the plastic. Yeah, usually very high melting and boiling points. Glass is very, very hard to melt, right? And they're very, very hard, but they're brittle for the same reasons that the other crystals are brittle, because the strength comes from the regular arrangement of atoms, and once you move it out of arrangement even a tiny bit, the crack can propagate through the entire thing. Yeah. Last is going to be metals, so let's set up for metals. Metals. Metals are weird. Keep in mind, you know, up here, the other crystals and networks will usually shatter if you try to bend them too far. And yet metal, right? This is made out of metal. This little jumper is made of metal, and I can just bend it, you know? I can bend it and it'll kind of hang in the same orientation. Or maybe, you know, this steel wool is, you know, no problem being bent and squished in all kinds of ways and twisted, you know, and it holds its shape, right? Try doing that with a piece of glass or a sugar crystal, or, you know, a salt crystal or a rock, because a lot of rocks are ionic compounds. You're not going to see it. You know, also, metals are conductive to electricity and to heat, right, compared to glass and to sugar and so on and so forth. They're also ductile. They can be made into a wire. That's what ductile means. You can put them into a wire. They're malleable. They can be hammered into a flat sheet. They can be bent. They will accept, you know, a lot of punishment. They're also very dense compared to other solids. And they will mix in any ratio for different alloys. So something like stainless steel is, you know, maybe it's mostly iron, but then there's chromium and manganese and stuff in it. And there's brass, which is an alloy of zinc and copper. And there's bronze is zinc and copper. Brass is tin and copper, I want to say. You know, all kinds of different things. 24 karat gold is pure gold. But you'll see jewelry made with 20 karat gold because it's got some silver in there, and you can put as much gold or as much silver as you want and mix them in in any proportion, so miscible. So why? Why do metals have these weird properties? Well, the dominant theory to explain the weird properties of metals is something called the electron C model. And to explain it, we can look at the periodic table and we can think, hey, metals have a low electronegativity. If a low electronegativity, they don't have a particularly strong hold on their valence electrons. And when you have lots of metals around, right? The theory goes, they all just kind of give up their electrons into a common electron cloud. This is called the electron C model. The valence electrons are delocalized. If you remember that word, delocalized from before, the electron can wander between different atoms, but in this case it can wander between literally every atom in the metal. The electrons are just free to go. It's like a kindergarten class, and all the parents drop off their kids and off they go all over the place. Or some people say that metals are communist because they just share everything. The electrons belong to the people. Electrons don't belong to any one particular atom, kind of thing. So this helps explain a lot of these properties. A lot of these properties are explained by this electron C. Right? Let's start with electrical conductivity. Why do metals conduct electricity? Well, you stick an electron on this side, all of the electrons move down, and an electron comes off the other side. So it's very easy for them to push electrons back and forth. Why are metals so ductile? Why can I take this and bend it and it's fine, right? It's fine. Why is it ductile? Because with an electron C, the bonds aren't rigid. You're not stuck in these rigid bonds like glass. There really aren't bonds to speak of, right? So you can bend a metal. You can bend it into shape, and it'll kind of hold that shape a little bit. Right? So that's malleable. Ductile, you hit it with a hammer, it flattens out into a small flat sheet. Same thing. It's not very brittle because it can just rearrange the electrons. The atoms don't really care what arrangement they're in, as long as they can keep sharing those electrons with each other. What else we have? Density. Density, because everything has released its electrons, the atoms, the positives can get closer together. They're not held at a certain length like these guys are, right? It's not held at a certain length. There's no empty spaces in the middle, like we see here or here. They can just pack in as densely as they want, kind of, until the electrical repulsion pushes them apart. But there's no set bond length for them to obey. And they can mix in any ratio because you can just stick another metal in, a different metal in, and it'll just give up its electrons to the electron C. Kind of like adding one more person to your communist society. Their property just becomes property of everybody else. That's the electron C model of metals. That isn't to say that metals don't form crystals. Metals do form crystals. Here's some examples. Here's a copper crystal. Here's a bismuth crystal. They're very pretty. Here's a gold crystal. Yeah, crystals of gold. Very cool. This is zinc that makes a crystal, and this is iron that's making different crystal structures. That's actually in a meteorite. They have different crystal structures. If you want to learn more about how metals form crystals, I recommend this video called Self-Organizing Steel Balls Explain Metal Heat Treatment. It's got a lot of very cool physical chemistry to it, and it explains a lot about how metal workers will heat up a metal before they work with it, and then heat it up again, and then heat it up again in order to make it tougher, make a tougher metal. So you watch that if you want to see an explanation about metal crystals. These are just steel balls in a thing that he's made, and you see they organize themselves a lot like these guys are organizing themselves. So cool example of metal crystals. Crystals are stronger because of that regular arrangement, and metal crystals are no exception. If you can make a solid crystal of a metal, you have a stronger bond, a stronger metal, even though it's just the same metal. Famously, this is done on aircraft engines. The blades, the fan blades in an aircraft engine, are grown out of a single crystal of titanium. One gigantic blade, huge blade, but it's one solid crystal of titanium. No grain boundaries at all, which is very, very cool. That's it. So in summary, ionic crystals are strong. They have a high melting point. They're often prone to cracking because of that cleavage. They crack along cleavage planes, very distinct cleavage planes. And a lot of them are soluble because water can just pluck out individual ions. Covalent crystals are weaker in terms of absolute strength, and they have a lower melting point because of it, because it's easier to pull apart dipole forces than it is to pull apart ionic forces. And they're variably soluble, depends on what kind of covalent molecule you have. Covalent network is very strong. It's an extremely large molecule. Like I said, this thing is just one gigantic molecule, billions, trillions, quadrillions of atoms. That's probably on the low end. They have a high melting point because it's just a bunch of individual bonds, but they are also very brittle because they have a regular structure. Then metal bonding has that electron C model, and they have all these weird properties because of it. They're ductile because the atoms don't really care where they are. They're lustrous, they're shiny. Oh, I didn't talk about shiny. They're lustrous because the electrons are everywhere and they're not stuck in a particular energy level. Remember, electrons absorb light and then kick out light of a specific energy level because they jump to certain energy levels. Well, metals, they're lustrous because they share all their electrons so much, they've shared them. There's no real distinct energy level there. The electrons can jump up and down to basically whatever level they want. This is called band gap theory. It's very, very interesting, banding theory. Meanwhile, these guys, because they're held in very regular arrangements and the neighbors are always the same, there's only specific transitions that are allowed. And this is actually why they're transparent, why you can see right through this flask. Because light, visible light, goes through this glass, and there's no electron transition that corresponds to visible light in this glass. So this flask can't absorb visible light because there's no proper electron transition. But that's a complicated thing called band gap theory. I'll find a video about it. I'll link that down below. So the lustrous metals are conductive because all of the electrons are just swarming. So if you put electrons on one side, all the electrons will move off. And so you'll end up conducting electrons through your metal. And they're also completely miscible with other metals. If you melt them down and make an alloy, it's fine because they're not actually bonded to each other. They're just sharing all of their electrons in this beautiful commune that they've created. That's it. It's a relatively short video today. And please look in the comments below, or in the discussion below, description below, for those links to the different things that I've been talking about. Yeah, that's it. This will be on the test, and I'll see you in class.